السلام عليكم ورحمة الله وبركاته. أسعد الله صباحكم جميعا. اليوم إن شاء الله مكملين معاكم بآخر سؤال من شابتر 18. وهذا السؤال الثاني لهذا section 18.5. So here in this problem we have 30 kilogram rod. So here is the rod, okay, OA, is released from rest when theta equal to 0. So here is the state 1. Okay, let me use pen. So here is state 1, and here is the reference also. So I will name this one as reference. Okay, and the rod initially was at this location, and here is the spring. Okay, so here is point A. Okay, so it's released from rest when theta equal to 0. Determine the angular velocity of the rod. So we need to find omega. Okay, when theta is equal to 30, so this is state 2. I can name it as theta 2, and this is theta 1. The spring is unstretched when theta equal to 0. So S1 at state 1 equal to 0. There is no stretching. The initial length of the spring is 0.5 meter. Okay, this is the length L initial of the spring when it's located at theta equal to 0. Why I judge that this is the initial length at theta equal to 0? Because it's mentioned that when theta equal to 0, the stretching is 0. Okay, so that means when it is at this state, then the length is equal to 0.5. Okay, and the rest is the length of the rod, which is 1.5. So here is 1.5. So the summation of 0.5 and 0.5 is 2 meters. So even trying to tell you that there is no stretching. So if the question did not mention that there is no stretching, this sentence was absent. Okay, then you can conclude from here that there is no stretching. Okay, because the initial length is 0.5. Okay, so here is the final answer, and here is, notice that U is the conservation of mechanical energy, which is T1 plus V1 equal to T2 plus V2. Okay, so the question is told us to use this equation. So let me go to the solving board. So here is the solving board, and let me write down the state 1 and state 2 conditions. So in state 1, here is the point where the spring is held, and here is the cord or the rod. Okay, so it's initially unstretched. Okay, so as we mentioned, this is 0.5 in terms of length, and this one is 1.1. Okay, this is all. In state 2, where theta is equal to 0, theta 1 equal to 0. State number 2, or do you know what? Let me calculate T1 and T2 and V1. So T1, which is the kinetic energy at state 1, is equal to half multiplied by mass multiplied by Vg1 squared plus half Ig omega 1 squared. I think you agree that this value is equal to 0. Why? Because in the statement of the problem, it's mentioned that the 30 kilogram is released from rest. So it is released from rest. That means V1 and omega 1 equal to 0, as well as T1. Let us look now at the potential energy V1. Potential energy V1 is consisting of V1 elastic and V1 gravitational. V1 elastic, which is always positive, half K S1 squared, and gravitational potential energy is weight multiplied by delta Y. Okay, so I think again you agree that this value is equal to 0 and this value is equal to 0. But why? Because in the problem statement it's mentioned that there is no stretching when it is theta equal to 0, which is state 1. Okay, so the stretching is 0. And again, this is 0 y, the gravitational, because it lies completely on the reference. So here is the reference as I mentioned earlier in the PowerPoint. Okay, so that means T1 and V1 is equal to 0. Now let's move to state 2. Let me again draw the problem. State 2. So here is state 2 when theta is equal to 30. So here is the first point where the spring is hanged, and here is the second point, and we name it O. Here is the spring stretched, okay, and here is the cord or the bridge. This is point. So this length is 1.5, and this is the stretching for the final length, L final. Okay, so we need to figure out S2 is unknown, okay, as well as omega. This is the omega 2, which is needed. Again, it's unknown, okay, and both of them, this is the reference, and this is 30 degrees. Okay, okay. Now let us first find T2. So T2 is equal to half mVg2 at state 2 squared plus half Ig omega 2 squared. Okay. Now this is equal to half multiplied by mass of the rod, which is 30, multiplied by Vg. Vg, we can benefit from the relation of Vg equal omega Vr. So this is omega 2 squared multiplied by the length of the cord, okay, or this is not the length, R represent the distance between the centroid and point O, okay, because this is rotation about fixed point. Okay, so I can substitute R as 1.5 divided by 2. Plus half the mass moment of inertia for the rod about the centroid is equal to, we can refer back to the uniform shapes. So 1 over 12 multiplied by m multiplied by L squared. So the mass is 30 and L is 1.5 square. Okay, multiplied by omega 2 squared. Okay, so this equation, by the way, if you substitute velocity omega multiplied by r, you can write it as half I with respect to point O omega squared. It will be easier. Okay, and you will find out the equation for IO for a rod about its end point, not about this rod. So this is equal. Let me use my calculator. So here what do we have? 1.5 divided by 2 squared multiplied by 15. So the right side is 8.4375 omega 2 squared plus. So here we have 1.5 squared multiplied by 15 divided by 12. So here we have 2.8125 omega squared or T2 oops, equal to plus 8.75 11.25 omega squared. I'll name this equation as equation 1. Okay. Okay. Now let's go to the potential energy. Let's open the sheet. So V2 again here is corresponding to V2 elastic and V2 gravitation. V2 elastic is equal to half, of course it's positive because it's at the same direction of the stretching. K, stiffness, and the value of the stiffness is given on the drawing, multiplied by S2 squared, which is unknown. And this one is equal to minus. Why it's minus? Because the rod is under the reference. Okay, so this is why it's negative. Once it is below the reference, then this is minus. If it's above the reference, state 2 above the reference, then it will be positive. Okay, but here is negative. So the weight is 30 multiplied by gravitational or gravity of acceleration or acceleration of the gravity, multiplied by distance, vertical distance, delta y from the reference. Okay, so here is the reference. Okay, and here is the chord. Here is the spring. This is 30. So I'm caring about this distance corresponding to the centroid. The whole length of the rod is 1.5, so half of it is 0.75. So I can easily figure out the distance y by using sine rule. So using sine rule, sine 30 is equal to y divided by 0.75, and from here this is 0.75. So if I use my calculator, sine 30 half multiplied by 0.75, which is 0.375 meter. So this value I'll substitute it upward. So here, still delta y. So let me erase it. So here I'll write 0.375, and this is equal to minus 110.36 joule. Okay, so this is gravitational potential energy. Now the remaining is S. So how to find S? Stretching. The stretching is this distance. Okay, here is the L final. We will name it L final. Okay. So how to calculate L final? Easily by drawing this triangle. Okay. So the whole distance is 1.5, and I need this distance. So if I name this y1, this would be y2. So let me calculate first y2, and you know that this distance is equal to 2. Okay. So also I can name this distance as x2, which represents this distance. Okay. So this distance represents 2 minus x2. So if I figure out x2 and y2, I can easily find L final. Okay. So let me first go and find y2. So using sine rule again, sine 30, but this time between y2 and 1.5. So from here y2 is equal to 0.75. Okay, 0.75 meter, and I'll use again cosine 30, which is equal to x2 divided by 1.2, and we can find x2, which is, so cosine 30 multiplied by 1.5, which is 1.3 almost. So now we can find the L final. So let me draw it again. So here is L final. Here is the dot. Okay, which is 1.5. Now here is the reference. This distance we could find it 0.75, and yes, 0.75, and this distance is 1.3, and the remaining distance out of 2, it's equal to 0.7. So 2 minus 1.3 is equal to 0.7. So L final will equal to 0.7 squared plus 0.75 squared. Okay, so using calculator, 0.75 squared plus 0.7 squared under root square is 1.426 meter. So the stretching S2 is equal to L final minus L initial. L final 1.026 minus L initial given in the problem statement 0.5. Then the final stretching is 0.526 meter. Okay, so here I should substitute meter. Okay, then this is S2. Now if I go to the top of this sheet, I will substitute instead of V2 elastic, instead of K, I write 80, which is the stiffness given the problem statement. So here 80 multiplied by S2, which is 0.526 meters squared. So using calculator, this is squared multiplied by 40, I'll get 11.06 joule. Okay, let me move to new page. So VT V2 total, which is minus 110.4 plus 11.06, I think. Then the answer is minus 99.3 joule. So this is V2, and I will name this equation 2. Now I will substitute equation 1 and 2 in the conservation kinetic energy, where T1 plus V1 equal to T2 plus V2. Okay, V1 and T1 equal to zeros. Okay, so here I write this is equal to 0, and this is equal to 11.25 divided by omega squared minus 99.3, and from here omega equal to 11.25 and the root square is 2.97, right? 2.97 rad per second. Okay, so here is the answer. So let me go back to the PowerPoint. It's 2.97. So that's it for this chapter. Now let's move to the new chapter. So here is chapter 19, the last chapter in this course. Okay, and again, if you can notice that the title of this chapter is the same as the chapters 16, 17, 18, planar kinematics of a rigid body. So still we are talking about rigid body. Okay, but this time we'll find the relation of the impulse and momentum. Okay, impulse and momentum. So sections of this lecture will talk about the first section, 19.1, and then we move to section 19.2, which talk about principle of impulse and momentum. But first we'll define and find a relation for linear and angular momentum. So both of these two sections are connected even in the book, so there is no separate problems for this chapter or for this chapter, so both of them combined. So this is why we'll talk about them today. So the objective is to develop formulations for the linear and angular momentum of the body. So this is the objective of section 19.1. We'll see how we can write equation for linear momentum, and it's simple, by the way, as L. Okay, and we'll see how to write the angular momentum equation, and it's simple as H. Okay, so and the objective of the second section is to apply the principle of linear and angular impulse and momentum. Okay, so now we have a principle of mechanical energy and mechanical and kinetic energy, and now we have principle of linear and angular impulse and momentum. Okay, so here is the application. The swing bridge. So this bridge, when it is in this arrangement, it allows for the vehicle to pass from this side to that side, okay? But when it starts swings, it allows the chip to pass to the other side or the opposite, okay? So this bridge is the swing bridge opens and closes by turning using a motor located under the center of the deck at A. So here is the motor located at this point, okay, and it applies a torque M to the bridge. So this torque will help the bridge to open and close. Now the question is, if the bridge was supported at its end B, so instead of A, we have supportment at point B. Would the same torque open the bridge in the same time, or would it open slower or faster? So if we replace the position of the motor up to this point, do we need same torque, same moment? It will open faster, slower in terms of time. So this is the first time we ask about time in this type of chapters, planar kinematics. Another question, what are the benefits of making the bridge with variable depth? You can notice here, this is the depth point, okay, but here is thin, okay. Well, is this shape affecting? Is the shape of this bridge affect the value of moment or not? So as you remember, when we are talking about shapes, we are connected it to the mass moment of inertia I. So is there any role of I in determining the required momentum or not? So by the end of this chapter, you will be able to answer these questions. Here another problem, okay? This is one of the experiments, this application, okay? But this is one of the experiments that you do in the civil lab, okay? Or material science lab. I think civil engineer, mechanical, industrial perform this type of experiment. We call it the pendulum. This is pendulum, but we call it Sharpie test. Okay, Sharpie test, or we call it impact test of Sharpie type. Okay, because there are two types. We have Sharpie and we have Isaac. So this pendulum this pendulum swings downward. Okay, as you can see, maybe it will start from here with this hammer. Okay. Then it will swing down, as you can see. Its angular momentum and linear momentum, as you remember, I'll call this parameter L as a symbol, linear momentum, and the angular momentum I will call it H. So as the pendulum swings downward, okay, كل ما اتجه للأسفل, the angular momentum H and the linear momentum L both increase. By calculating its momentum in the vertical position, we can calculate the impulse the pendulum exerts when it hits the specimen. Okay, so a specimen I will delay talking about it up to next section 19.2. Okay, but here take a look to the values. So this value, for example, mass multiplied by velocity of the centroid. So here is the centroid, and you know that this point is fixed, okay? And the velocity of this point is tangent to the curve because this is rotation about fixed point. So if I multiply this velocity by mass, as you will see in the next slide, we'll call this value as linear momentum L, and you can tell easy that the value that this L has magnitude and direction. Magnitude is mass multiplied by velocity, and direction the same as the velocity direction. Okay, so both L and velocity, they will have same direction. As a magnitude, it's mass multiplied by velocity. Now the other component, which is angular, from its name, and we give it symbol h. It's connected to the omega. So if I multiplied omega by ig, then we can call this value or this magnitude is h. So h again is a vector. Its magnitude is I multiplied by omega. Okay. So it is I mass moment of inertia multiplied by omega. Here, the importance of shape omega I, sorry, mass moment of inertia. This is why shape of the rigid body is important. Okay. So if I multiplied omega by Ig, we can name this as h. So as a magnitude, it's I multiplied by omega, as the direction is same as omega. So the direction of h is, which is angular, it will be counterclockwise in this scenario. So here is another rigid body, okay, and this rigid body, the centroid moves in this direction, velocity. So if I use xy coordinate system, then this velocity has x component, m multiplied by vgx. So I can call this one again lx. And we have vertical component m multiplied by vgy, and I can call this one ly. Or the summation is under root square is L, which is equal to mvg, and both of them is bold. Okay, so the linear momentum, again this symbol is bold, it means this is a vector, okay, is defined as L, which is equal to mass multiplied by velocity vector of the centroid. So this equation says that the linear momentum vector L has a magnitude equal to mass multiplied by Vg. So here is the magnitude, and the direction defined by Vg. So same direction. Its unit is very simple. So here is meter. So the velocity is meter per second. Okay, and the mass is kilogram. So the unit is kilogram multiplied by meter per second. Or this is in the English units, like multiplied by 4 divided by 7. The other component, the other very important component is the angular momentum, h, okay, of a rigid body, which is defined as hg equal to ig multiplied by omega. Okay, this equation we can get it after doing certain derivation or after certain steps. So usually we start with this equation from here. Okay, so either we can benefit from this equation in order to find the angular momentum, or we can use this one. Okay, you will end up with this equation, as we'll see in the coming slide. So hg is a vector quantity having magnitude ig multiplied by omega and direction defined by omega. So it has same direction for omega and as a magnitude ig multiplied by omega. And regarding its unit, this is rad, or 1 over second, rad per second, or 1 over second multiplied by kilogram multiplied by meter squared. So as a result, it is kilogram meter squared over second, or in terms of English unit, this is the unit. So as I mentioned, this is a vector, okay, for any arbitrary point. So you can notice that this is the mass moment of inertia about the centroid, but we can start derive this equation from arbitrary point, name it as B. Okay, so if I want the angular of momentum of point I from an arbitrary point B, so here is the point I on a rigid body, and it is far away a distance r from arbitrary point B. Okay, so the equation or the derivation start using this equation. So mi vi, which represent L. So if I multiply the linear momentum L cross product with the relative position vector r, and if we substitute instead of r the direction and the magnitude, which is x in the I direction plus y in the j direction, because you know that this r consists of x component and j component until reach ith point. Okay, and this is cross product vi. Vi again, this is relative velocity, or the velocity, absolute velocity of point I, but we can benefit from the relative velocity, which is Vb plus Vi with respect to V, and substitute omega. So if we do this derivation, okay, we'll end up with this equation. Okay, and take the integration, of course, we'll end up with this equation. Now, this equation, if point B is coincides with the centroid G, then again this term and this term go to 0. Why? Because if point B and G identical, then there is no distance. So as you remember, x dash means the distance between any point with respect to centroid. So if this point B and G same, so this equal to 0, and again this one equal to 0, and we end up with this value. Now compare this equation with this equation. So instead of G I can write, instead of B I can write G, because they are coincides. So here is the final formula. So either we'll benefit from this equation, okay, or we'll start from this equation. Why? Because if we multiply the linear momentum here, you can tell easily. This is, we call it L, remember? So if I multiplied L by this distance, this is multiplied by D, you can call it H. Okay, so either D multiplied by L, or directly I can say IG multiplied by omega. Okay, so here I may add to keep things consistent. Now let's see the scenarios. You know that the rigid body has translational, rotational, and general plane motion. So if we have translational and we wish to find linear and angular momentum, you can notice that the linear momentum is equal to mass multiplied by V, because here we have translational, and translational happen at a certain velocity. But since we don't have any rotation, then the hg will goes to 0. Okay, this is in general. This is if we talk about if we wish to find angular and linear momentum with respect to g. But if we take it about any other point except centroid, we'll have different story. We'll come back to it. Okay, so this is in terms, we'll see the equations first in terms of the centroid. So let's move to the rotation about fixed axis. So if I wish to find linear momentum with respect to centroid, which will have certain velocity, then the linear momentum equal to mass multiplied by vg. If this type of motion with respect to a body that is fixed at the centroid, the linear momentum will goes to 0. Why? Because the fixing point happens at the centroid. But if the fixing point, the fixed point on a rigid body, any point except centroid, then L will be equal to mvg, and hg will equal ig multiplied by omega. Now remember that we'll see the equation first with respect to centroid. Okay, so if we have general plane motion, then we'll have linear momentum and angular momentum with respect to centroid. Now, if we consider any other point, for example here, if I need to find linear momentum and angular momentum of point A, any arbitrary point, then LA will remain as is, okay, and the only thing might change is H with respect to A, because now we have a distance, okay, between the linear momentum and this A, which is the angular momentum of the centroid was 0, but now the angular momentum of point A become d multiplied by mg. Now here the same. If I need to find the angular momentum about O, what I'll do, I'll do cross product between Rg and mvg. Here it is. Okay, it is Ig omega plus Rg mvg. Okay, so here instead of vg, I can write Rg omega. So here we have R, then R multiplied by R, it will be R squared. If I take omega as a common factor, we'll end up with this brackets, which is from parallel axis theorem. Then this is IO omega. So in terms of angular momentum with respect to O, this is the equation, or we can write this equation, okay? Because about point O, we have two source of angular momentum. The first source is the rotation of the centroid, and the second source is the cross product of distance r perpendicular on the linear momentum. Okay, so we add them together. Now the last but not least, if we have general plane motion, then we'll have three scenarios. Either we'll take the angular momentum with respect to centroid or any arbitrary point. So the case will be similar to the rotation with respect to this this one. Okay, and the third scenario, if we have IC, it will be the same. Okay, so we'll end up always with this conclusion. Okay, here we have example. Okay, before moving to next section, but I'll delay this example to next lecture. Okay, so you can try to solve this example by your own self. Until then, stay safe and see you soon.